All right, everybody, here we are again for another exciting episode in our Geology 1 lecture series. Thank you so much for coming back. And this is really kind of a part 2 continuation of our last module, our discussion on igneous rocks. Last time we introduced you guys to the rock cycle. We introduced you to the different types of rocks and we defined those. And then we focused in on our igneous rocks. And we talked about that we need two things to identify. We needed to know two things to identify any igneous rock. And those are that igneous rock's texture or grain size, right? And composition. So last time, in our last module, we went through a bundle of different igneous rock textures, noting that our igneous rocks, we can really, by looking at those textures, we can place them into one of two categories, either intrusive or extrusive igneous rocks. Those are our options, intrusive or extrusive igneous rocks. And again, what that will impact, where those materials cool, what that impacts is grain size, right? The size of the mineral grains or the texture, right? So again, those two broad categories for intrusive and extrusive igneous rocks. And so now today we're going to start discussing the chemistry of these materials, that other component that we need to identify these rocks. So we're going to talk about Bowens reaction series and this interesting history of the development of this idea of how igneous rocks gain their specific mineralogy, their specific chemistry. Namely, we're going to talk about, or in addition to that, we're going to talk about the ways in which we get different rocks out of the same molten mass. Isn't that weird? The same molten material can produce many different types of igneous rock based on their chemistry. They will have very different chemistries. So how does that happen? And then we're going to talk about some examples of igneous rocks and where we find them, different chemistries, different textures, and those sorts of things. So lots of fun to be had, tons of exciting things to discuss. And as always, I am here. I am here. If we're going through these things and you're running into questions or those sorts of things, as always, I'm going to remind you, utilize those Canvas resources. Send me that email. Let's set up that Zoom, whatever it takes. Let's make sure that you've got all this stuff squared away so that you can knock those quizzes, those exams out of the park. Truly, I want to see that happen. And the way we do that is through communicating. So let's do that. All right, everybody. So with that said, again, this is part 2. We're talking about the composition of different igneous rocks. So we also classify our igneous rocks based on their chemistry. And so we have a few different categories for different chemistry of igneous rocks. That is, we've got, just like we had with our texture, we had two categories. Underneath our chemistry column, we also have multiple subcategories. So the first of those subcategories, you've heard this term before in this class as we discussed plate tectonics, that is felsic composition. You might remember when we talked about continental crust, we said it has a felsic composition. And here's that term again. What that's referring to are the materials, the igneous materials within that continental crust. They have this granitic or felsic composition, which means that it has a lot of feldspar and quartz in it. Lots of feldspar, lots of quartz, lots of these silica-rich materials. You've also heard this term, mafic. Mafic has a slightly different chemistry than our felsic materials. Mafic materials and felsic materials will both have some proportion of their mineralogy will consist of silicate or silica within them, silicate minerals within them. However, for mafic materials, as we discussed, they have a whole bunch more magnesium and iron. Magnesium and iron, thus that term mafic. Typically, because of these more magnesium and iron-rich materials, right, these iron-rich materials, these magnesium-rich materials, are typically going to be darker, and they're also going to be more dense. And you might remember that that's why the seafloor, why our oceanic crust, right, has a higher density than our continental crust. All right. And so again, these are the materials that we commonly find not only along the ocean floor, but also in volcanic islands as well. Oftentimes we'll extrude these very dark colored mafic igneous rocks. So these are two categories for chemical composition, but I want to note that there are at least four. So between felsic and mafic chemical compositions, there's actually an additional category that we're going to discuss in this class called intermediate igneous rocks. These are intermediate to felsic and mafic. They're kind of between the compositions of these two things. So an intermediate rock is going to have some felsic components, some felsic minerals, but also some mafic minerals. On the other side of mafic, we can also have ultramafic rocks. Ultramafic rocks are rocks that contain minerals that are very high in magnesium and iron, really high in magnesium and iron, these ultramafic materials. So those are the four categories for igneous chemical composition that we're going to talk about in this class: felsic, intermediate, mafic, and ultramafic. We're going to see those come up here again. Why? Right? Why? Why are our continents made up of the stuff they're made out of consistently? And why is our seafloor made up of the stuff that it's made of consistently? What on earth is driving the chemistry in these materials when these molten materials solidify? Why does it work? Well, it works because different minerals crystallize or solidify out of that molten mass at specific temperatures, which depend on what they're made of. Isn't that interesting? That in that magma chamber, you have all the ingredients that you need to make a whole bundle of different types of rocks. And as that magma chamber goes through its cooling history, or that magma chamber is present in different environments, maybe within oceanic crust or versus continental crust, those different environments yield different temperatures and different rates of that temperature change, which ultimately result in these elements coming together at different times in the history or in the evolution of a molten mass, which again will yield different rocks. And really interestingly, this is all a chemistry and physics experiment that's going on here that is predictable and repeated over and over again. That is the crystallization sequence, the sequence in which these minerals will crystallize out of that molten mass. That happens in a very specific order, and that order is referred to as, you guessed it, or maybe you read it right here on the slide, Bowens reaction series. Bowens reaction series. So Norman Bowen, a geologist working at the Carnegie, was interested in igneous rocks and all sorts of minerals and all kinds of stuff. And in his work with igneous rocks, he noted two really important observations. I love these ideas that come down to some really just fundamental observations and then going, why at the end, right? There's so many opportunities for that in geology. It's just such a beautiful thing that there are so many whys that still sit out there. And this is a great example of somebody pursuing one of those with some really just fundamental observations. One, Bowen and his team recognized, hey, there's a lot of different minerals out there with a bunch of different chemical properties, but they're all going through this same process of going from molten material to solid. That's weird, right? That's really weird. The second observation was that a single magma chamber can produce multiple rock types. That's weird too. I mentioned in the last module there my fondness for barbecue, for barbecuing. I also am quite fond of baking. I'm not like a pro at either of those things, but I find them fun. And so I imagine myself in this situation. You're baking and you take essentially all of the stuff that is in your cupboard and you throw that into a big mixing bowl and you go ahead and you stir that up and you get yourself a solution of just gobbledygook in there, right? Just all of the things that you would use to make everything you could ever think of. And you take that big giant mixing bowl, you pour that into a baking dish and you put that baking dish into the oven, and all you do is you sit back and you wait. And then suddenly you open that oven, and rather than that big giant mixture thing that you made just becoming a big block of solid, instead, when you open the door to the oven, you look in there and there's a turkey. Next to the turkey is a pumpkin pie. For some reason, I'm Thanksgiving theming this. There's some cranberry sauce, right? There's all sorts of interesting things in there that have all separated themselves out, become very organized out of that same mass that you made. How is that possible? And that's how Norman Bowen was viewing a magma chamber, was how do you look at a magma chamber and then get all this different stuff to be well organized, right? But very different things out of the same molten mass. How does that happen? So Bowen and his team were convinced that there's got to be something happening, right? There's an external factor that's influencing how these minerals are crystallizing. And then there's got to be some mechanics for how that molten mass is changing through time. There's got to be something that's resulting in those ingredients changing through time. And what so much of both of these concepts can be answered by are changes in temperature inside of a magma chamber. So what Bowen recognized, right? Bowen and his team went to work and recreating the conditions that were required to produce each of the minerals that they were finding in their igneous rocks. And for a select set of those minerals, they saw that these things were crystallizing out in a predictable and repeated sequence that was related to changes in temperature. That is, at very high temperatures, in a molten body of rock at very high temperatures, minerals that were rich in iron and magnesium, those things started to crystallize out first. Minerals like olivine, which we saw in our Matter of Minerals lecture, is a perfect example of that. And so as temperature fell, they noted that as that iron and that magnesium was depleted, different minerals started to form. And that process continued and continued and continued, where at different ranges of temperatures, different minerals were forming in the magma chamber. And so ultimately, what we see in our igneous rocks, our different igneous rock compositions, are a collection of minerals that solidified at the same temperature. And we can take that framework and we can divide it into a few different parts. That is, if you look at this graphic, what you're seeing is on the left here, if we were to think about this entire graphic as being a recipe, on the left here, that recipe gives us the temperatures that we're going to need to have as we bake our rocks, right? That is, on the left there, we start out with our oven at a very high temperature, and continuously we just keep cooling it off through time. In the middle here, right, are the ingredients. This is our molten body of rock. So as we start to turn down the dial on our oven, at the highest temperatures, things like olivine, plagioclase, feldspar, pyroxene, these are the things that are going to start to appear in our molten mass there first. Sequentially, all the way down to quartz, which will quartz, potassium feldspar, and muscovite, which will all crystallize out of this molten mass last. They'll be the last things to come out. On the right here, we see our products. That's what we get, right? And those are our different igneous rock type compositions. So a few things that I want to point out to you all here in this graphic. The first is in this last column, in our igneous rock types, I want you guys to note that our chemical composition headers are given for each of these boxes, right? You see felsic there at the bottom, intermediate, mafic, and ultramafic all the way to the top. Those are our chemical composition categories. But then within each of those categories, you see in parentheses those rock types: granite, rhyolite, diorite, andesite, gabbro, basalt, and peridotite, comatite. So there's 2 rocks listed for each of these compositions. And there's 2 rocks listed because each of these rocks are the intrusive and extrusive equivalents of each other. What I mean by that is granite and rhyolite. Granite is an intrusive igneous rock, right? So describing that rock's texture, we said, was the first part of identifying our igneous rock. So if we saw a piece of granite, we would describe its texture, and we would say, be able to say, in doing so, this is an intrusive igneous rock. If we saw a piece of rhyolite and its texture, we would say that's an extrusive igneous rock. So granite, intrusive; rhyolite, extrusive. They are different rocks because their textures are different from each other, but chemically, they're identical. Isn't that weird? They're both, for chemical composition, they are identical. Both granite and rhyolite contain potassium feldspar, muscovite, and quartz. The only difference between these 2 rocks is their texture. And so in each of these rows, under each of these chemical composition cells, intermediate, mafic, and ultramafic, you see both the intrusive and the extrusive equivalents of each other. So diorite, intrusive; andesite, extrusive; gabbro, intrusive; basalt, extrusive; peridotite, intrusive; comatite, extrusive. And I'll note that comatite as an extrusive igneous rock is really, really rare. It's really rare. And the reason why I point that out is because it helps make us some connections with Bowens reaction series. We see that comatite, the minerals in the comatite there, maybe some olivine, maybe a little bit of pyroxene, and some plagioclase feldspar there, calcium-rich plagioclase feldspar there. Those minerals, they solidify at a very high temperature. And in doing so, in solidifying at that very high temperature, it's really difficult to maintain a molten body of rock at those high temperatures anywhere near Earth's surface. The only way to do that is to bring this stuff up remarkably rapidly in these volcanic type eruptions, explosive type eruptions that produce these what are effectively pipes of these this comatite material. Again, this stuff forms really, really, really quickly. You've got to get this stuff to the surface really quickly. Otherwise, it's just going to start solidifying, right, in Earth's interior. So you might get some peridotite instead. Kind of interesting. All right. So that's one thing. And again, so we're seeing intrusive, extrusive for each of these chemical compositions. Looking at the ingredients list, we can't help but notice too that there's this kind of Y shape to the ingredients list. That is, olivine, pyroxene, amphibole, and biotite are all separated from each other by individual arrows. This side of the graphic is referred to as the discontinuous series of crystallization. That means when you have that molten mass and it starts to cool, the first thing that you're going to get is some olivine. That olivine will continue to crystallize out, and eventually, in addition to the olivine, you'll also get some pyroxene will start to form. Then that pyroxene will start to crystallize out by itself. Then eventually you'll also start getting some amphibole that's crystallizing out at the same time as the pyroxene. And then all of amphibole will eventually be joined by some crystallizing of the biotite mica. Right, so these are separate ingredients that, again, sometimes have overlap in their crystallization pathway. That's in contrast to plagioclase feldspar, which is on the continuous series of crystallization. Plagioclase feldspar includes a whole bunch of different types of minerals. Those minerals that crystallize at a very high temperature of plagioclase feldspar that crystallize at a high temperature are going to be very rich in calcium. If the plagioclase that solidifies at a lower temperature is going to be rich in sodium. So between those two end members is a mixture, is plagioclase feldspar that contains a mixture of calcium and sodium. And this mixture can sometimes produce some really interesting things. A relatively common form of plagioclase feldspar is something called labradorite. Labradorite, I see it in kitchen countertops sometimes, has a generally dark color, but if you look at it relatively closely, you'll see it has like an iridescence to it, kind of a purplish, greenish iridescence. It's really pretty. So if you see that while you're out and about, maybe looking at some labradorite, again, a type of plagioclase feldspar, which is kind of in the middle between that calcium and sodium rich end members there for that continuous continuous series. There then in the trunk are potassium feldspar, muscovite, and quartz. There are really felsic materials, and we're going to see that kind of stuff all the time in the Riverside area here. If you take a hike again in the Box Springs, the San Bernardino Mountains, portions of the San Gabriel Mountains, you're going to come across quite a bit of granite. And so great way to identify granite. If you're seeing a rock that contains lots of pinkish minerals alongside with maybe some white colored minerals and some dark colored minerals, that's going to likely be some sort of granite or maybe a granodiorite. Sometimes they, for some of these rocks, you'll see intermediate forms. So a granodiorite is an igneous rock that kind of has a felsic / intermediate composition, but definitely down here in the lower end of this graphic. Another important thing to point out is over here on the right. And what we're seeing is that, again, at these higher temperatures, these are rocks that are going to contain lots of magnesium and iron relative to their silica content. Down at the bottom of the graphic, less magnesium and iron, much more silica. Also much more aluminum in these lower ends of the Bowens reaction series. So again, as you can see, the rock type, it captures a specific temperature, right, at which these molten materials, they cool and they solidify. And so these minerals crystallizing in a predictable sequence, right, allows us to, again, say something about the rocks in which they form. By looking at the mineral composition of these rocks, it certainly speaks to the chemistry of the magma chamber, but also the temperatures at which that magma chamber may have cooled and solidified. Again, minerals are the building blocks of rocks. And as these minerals form and collect, they are forming different rocks that reflect these different temperatures at which the magma chamber was at. Here's another really interesting thing. You guys have seen these minerals before. You saw these minerals when we talked about matter and minerals. And if I'll maybe jog your memory a bit. When I said, when we talked about olivine, we talked about it as a silicate mineral. You may remember, or do you remember, the type of silicate mineral that it was? It was a single tetrahedron silicate. You've also seen pyroxene, which is a single chain silicate. You've seen amphibole, this double chain silicate. You've seen biotite, this sheet silicate. And then you've seen these framework silicates down here at the bottom, quartz and potassium feldspar. These materials that form these dense three-dimensional network of tetrahedra. So what are we seeing there? Yeah, maybe an aha moment. Isn't that interesting? What's happening is as these temperatures are cooling, they're allowing more and more covalent bonds to form between these materials. So these high temperature materials like olivine are going to have fewer covalent bonds, whereas these lower temperature quartz and potassium feldspar are going to have more of them. So what's your prediction then for the susceptibility of these materials to erosion? That is, if we look at the rocks that these things ultimately come together to form, peridotite, gabbro, diorite, granite, what do we think about the resistance to erosion for each of those rocks? Fewer covalent bonds with their single tetrahedron means weaker bonds, which means ultimately weaker rock, higher susceptibility to erosion. You go down to the beach, right? If you visit the beach, let's picture ourselves, we're sitting there, we're digging our toes into the sand, right? It's a beautiful day at the beach. Always fun to try to picture ourselves at the beach, right? And you look down at that sand and what does it look like? What color is it? And you might say, well, Sappenfield, I don't know, it's kind of a pinkish color. It's mostly light color. And I would say that's exactly right. Well, the rocks for that sand are the rocks that are all in behind us. And if you looked in those rocks that are there in behind us, you would see that those rocks certainly contain those lighter colored minerals, but they carry a lot of that dark stuff too, that more mafic material as well. So why is the sand at the beach so pale in color? This is why. This is why, right? Is again, these mineral properties and the covalent bonds that these more mafic materials lack makes them more susceptible to erosion, more susceptible to being broken down on their trip from the mountains to the beaches. That's what's going on. And you can see examples of Bowens reaction series and the things that we know about matter and minerals. We can see them in all sorts of observations we can make in rocks. If you take a hike in the Box Springs, you'll find rocks that may have a considerable mafic component, maybe lots of amphiboles in there. But you may also see in and among those rocks big pink minerals jutting out from the side of that rock, like a knob sitting out there. And what's going on is that more mafic material within that rock is eroding more easily than that pinkish colored potassium feldspar that is a framework silicate. So it continues to stick out as it's more resistant to erosion. We can see that in an individual rock. We can see that in a mountain range and the weathering patterns that we see across different types of rocks in a mountain range. Again, Bowens reaction series coupled with what we know about these covalent bonds manifests itself out really significantly and at a variety of scales. It's really neat stuff. And we can actually look at this and the chemical composition of these rocks in perhaps some additional detail, maybe a little bit more closely, a little bit more precisely, rather than simply saying that a granite contains potassium feldspar, quartz, and muscovite. It'd be nice if we knew how much of those materials were actually in a granite, what percentage of those materials. And that's what this graphic allows us to do. This graphic looks different than the Bowens reaction series that you just saw, but it's showing us the same exact information. However, now we're adding in a percent by volume characteristic to our graphic that allows us to not just know for a recipe to make cookies, you need butter, you need some sugar, you need some vanilla, some flour, right? This graphic tells us how much of those ingredients each of these rocks contains. What's the proportions of these things that they contain. So right there at the top of the graphic, we have our 4 categories of igneous rock composition: felsic, intermediate, mafic, ultramafic. Underneath that row, we have the actual rock types. And again, in that intrusive, extrusive sequence: granite, rhyolite, diorite, andesite, gabbro, basalt, peridotite, comatite. Below that portion of the graphic then are all of those minerals that go into those rocks within that column. That is, for a felsic igneous rock, it is going to be made of these minerals in these relative proportions. So some granite may have very little potassium feldspar, but a whole bunch of plagioclase feldspar. Some granite may have a lot of potassium feldspar and only a little bit of plagioclase feldspar. But granite most certainly won't contain any olivine. Right? Intermediate igneous rocks are going to have a lot of plagioclase feldspar, a significant amount of amphibole, right? But they're not going to have any muscovite. Mafic igneous rocks, a fair amount of plage, a little bit maybe sometimes of amphibole, sometimes not, right? A fair amount of pyroxene, and maybe even a little bit of olivine in there as well. Our ultramafic rocks are going to have lots of olivine in them, a fair amount of pyroxene, some plagioclase, but certainly no quartz. Down here at the bottom, again, we see the changes in the silica content along these rocks, changes in the iron and magnesium content, as well as calcium. Calcium, we remember, for in our plagioclase feldspar, that higher temperature material. Here on, there's an additional arrow put in here regarding potassium and sodium. More potassium and sodium as we move into these cooling rocks and minerals down here. And then again, our temperature at which melting begins for these various rocks. So again, this is a recipe. And what I want to give us the chance to do is figure out how we would bake these materials, how we would make them. So we're going to do an exercise together right now. And it's one that you most certainly want to take notes on. You can print out this slide if you want to, or you can print it as a PDF and work on top of it if you want to practice that way. But I want to let you know that questions or a question on your quizzes or your midterm or your final exam, you might see something like this. And so something that's definitely worth your time in making sure that you have this system down. All right. All right. All right. So we've got here at the top, this is something, again, is made to kind of demonstrate the way we need to know this for your future assessment items. So here at the top, we have that composition table, and we noted that these are our composition categories. So we got felsic, intermediate, and then, a blank. So what goes in this blank? Well, we know that is mafic goes in this blank here. I'm going to reduce the size of that a little bit there. So mafic goes in that blank there, and then ultramafic. So we filled that in. So now we're going to fill in the rock types. We can start with the intrusive igneous rock types, right? So we've got granite. Right here, we've got diorite, right? Right here, we've got gabbro. And then right here, this very last one, we've got peridotite. Those are the intrusive rocks. Now the extrusive rocks. We've got rhyolite. We've got andesite is already given for us. So we've got basalt. And then we've got comatite. All right. So granite, diorite, gabbro, peridotite, rhyolite, andesite, basalt, comatite. This is the first thing that you want to do. Make sure that you have this table completed, ready to rock. Now we move down, we've got, now here's our recipe, and these columns again line up with the columns that we have for each of our chemical compositions. And it says here, step 1, answer the questions below using both the table you just filled in and the table below it. So this table here and this table. The rock we are looking at is an extrusive felsic igneous rock. So extrusive, there's texture. Felsic, there's composition, igneous rock. So is this rock fine-grained or coarse-grained? Well, we know to determine fine-grained or coarse-grained, we're looking at texture. And if the texture is given as intrusive or extrusive, that'll allow us to answer this question. Intrusive is going to be coarse-grained. That's right. Extrusive is going to be fine-grained. Fine-grained. All right. So this is a fine-grained igneous rock. So we are working here, extrusive felsic igneous rock. We are looking at a piece of rhyolite. This is a piece of rhyolite, right? So we could say, if we wanted to, we could add in here the rock type. We could say, well, this is a rhyolite, right? That's what we're going to be describing as a rhyolite together. So now what it says to do is in the blanks provided below, list out the minerals present within that rock type, as well as the percentages of each mineral within the rock. Note that you may or may not use all of the blanks. Okay. All right. So let's take a look. How are we going to do this? Well, the way that we're going to get the recipe for our rhyolite is we're going to work within the rhyolite column. And we note that, again, the relative percentages of each of these minerals, it changes, right? It changes through this entire column. So what we're going to do, let's just go ahead and we're going to pick a rhyolite that is kind of right in the middle of the column. And the way we choose that rhyolite is we draw a vertical line. Step one, draw a vertical line through the column. All right, draw a vertical line the length of the column. Now what you're going to do is where that vertical line intersects any mineral, right? Any mineral category, we're going to go ahead and we're going to draw a horizontal line over to our y-axis. A horizontal line over to our y-axis. For every time one of these minerals here crosses this line. All right? For every one of them that crosses this line here. All right. So now each of these categories here, right? That tells us which minerals are included in the rock. So we can go ahead and list those out. So first, if we start from the bottom, we have some amphibole, right? There's some amphibole in there. There's some biotite in there. There's some muscovite in there. There's some plagioclase in there. There's some potassium feldspar, oftentimes written as case bar, and we're actually going to need one more blank here because there's a little bit of quartz as well, right? Fair amount of quartz, I should say. So again, amphibole, biotite, muscovite, plagioclase, potassium feldspar, and quartz. There's no pyroxene, right? Because pyroxene doesn't intersect our line. There's no olivine because, again, olivine doesn't intersect our line, okay? So that's our first job, is to list out the ingredients. Now, our second part of the job is to list out the approximate percentages of the rock that each of these ingredients represents. And the way we do that, we see that percent by volume, it's 0 at the bottom, 100% at the top, right? So 0 to 100% of the rock is what we're describing. And so if we look at the percentage of amphibole, we just look at where how much of this percentage column is captured within that amphibole window, right? Within this little interval here. And we just have to give an approximate, maybe just rough percentage. And I'm going to say something like maybe 7% or so, it looks like. Let's make it, why not? Let's make it 8. And again, just rough estimate, okay? So 8% of this right here, this little window right here is 8% of our total column. So now our next columns, biotite and muscovite, we see that they bring us up to just a little bit below 20 there, and they do so, in about equal amounts. So if we're going from, let's say, this point right here is 8, and this point right here below 20, that's going to be about 18%, right? But note that biotite, muscovite, they're not 18% of the whole rock, right? That is, they're only this little window right here and right here, right? They're just that thickness, right? They're about the same thickness there. So it goes from 8 to 18. We know that this total thickness right here is about 10. So that's probably about, for each one of those, about 5% each. 5% each. So 5% there, 5% there. Okay. 5% there, 5% there. So now that brings us to here. Now our next mineral is plagioclase. And so we go from 18 to what it looks like, maybe it's a little bit below 40. Let's just, for simplicity, let's call it from 18 to 38, right? So all we got to do is 38 minus 18. That equals about 20%, about 20% or so. All right, so now we're sitting here at about the 38 part, right? 38% we've described so far. If you were to add these up, 20 plus 5 is 30, plus 8 is 38. That's where we're at here on this column. Now we got to get up to the next line. And that, it looks like it's just a little bit below 80. Let's call it 79. All right. So now all we have to do is 79 minus 38, right? 79 minus 38. That's going to equal about 39%. Oh, excuse me, 41%. 41%. Right? 41%. So 41% of this rock is potassium feldspar, right? 41% of that rock is potassium feldspar. Now, right, the rest of the rock is quartz, right? The rest of the rock is quartz. So what we're going to do, let's go ahead and add up all of these, and they should add up to about 79. So let's do that. 20 plus 5 is 25, plus 5 is 30, plus 8 is 38, plus 38 plus 41, that equals 79. So all we have to do now, we were at 79, we just got to take 100 minus 79, and that's going to give us the approximate percentage of quartz in the material, and that's going to be somewhere around 21%. And that's our recipe. So this particular piece of granite, or excuse me, rhyolite that we described here, right, consists of 8% amphibole, 5% biotite, 5% muscovite, 20% plagioclase, 41% case bar, and 21% quartz. That's the recipe for this material. And you can see that if we were to do this same experiment, but move this line over here, we would get slightly different percentages for each of those minerals. If we were to move it over here, same thing, right? So these things vary a little bit, and going in the middle of the column here, that just allows us again to get kind of a middle of the road example of this rock. And we can do that again for any of these columns. Same exercise, right? Same exercise. See where those cross, draw the horizontal lines over, list those ingredients, and give those relative proportions. All right? That's the process. And that's a process that you want to be able to do for each of these columns. In fact, if you wanted to, you could do that for all of the rock types that you have listed here and have that information in your notes. And if you wanted me to check any of those or give you any feedback, that's exactly what I'm here for. Awesome. So then the last question here says, what other rock is the same as this rock in terms of composition? That is, what other rock other than rhyolite would we describe with the same exact chemistry? What other rock would we do that with? Well, we would do that with the intrusive version of that rock, right? Same chemistry, it's in that same column. So that would be granite. Granite. All right. Awesome. Awesome. All right, everybody. So again, I'm here if you need any help with that kind of stuff, more than happy to go through it. This is, again, an important skill, an important topic to discuss here with Bowens reaction series. So make sure you have this one down. It is likely that you'll see these come up, or something like this come up on a future assessment. Awesome. All right. So then moving forward, let's continue with thinking about Bowens' dilemma. That is the second part of that dilemma, that a single magma chamber, that a single set of ingredients can produce both a gabbro and a granite. What on earth? How is that possible? Same ingredients. Why are we producing these different things? Well, that's because magma chambers, they go through their own evolution. A single volcano, a single magma chamber may produce different rocks, different lavas in 3 different processes. We're going to discuss each one of these in detail. The first is magmatic differentiation. The second is magmatic segregation. And the last one is assimilation and magma mixing. So you can write these terms down in your notes if you want to leave some space between them, or however it is you take your notes. That might be a good idea here. And so we're going to start here in thinking about a magma chamber and what's going on down there in relation to Bowens reaction series. And a great way to do that, as I know I've mentioned in this class, one of my favorite things to eat is soup. I love to just take, all of those veggies and just put them in a broth and make soup. So it comes up as an analogy quite a bit. And so we're going to consider then a warm bowl of magma soup. And I want to introduce you to 2 of the pickiest eaters that you could ever imagine, but 2 of the most adorable individuals that you could ever imagine as well. These are my kiddos. And as a testament to their pickiness, I will call your attention to the plates there in the foreground. This picture always cracks me up because I see my son has avoided what looks like maybe some delicious mashed potatoes or something like that, and has also only eaten the very, very center of his sandwich, because crust is absolutely disgusting when it's in a turkey sandwich. But if it has peanut butter on it, I guess then it's delicious. I don't know. It's just reasons. They're just reasons. Those that have kids know exactly what I'm talking about. Just, reasons. My daughter there went through a stage. I think we're through this stage now, but there was a stage where she would only eat the tops of the muffin. She wouldn't eat the bottoms of the muffin, which I feel like I remember was also a Seinfeld episode, but I was living it. And so we had these little muffin filled muffin cups all the time, But these 2 little ones are pickiest eaters. And we're going to imagine that I'm preparing this warm bowl of soup for them and their nutrition. And so as we do, we pour our hearts and souls into the things we prepare for our little ones. And I spend time going to the store and getting all of these ingredients that we need for our soup. And I put that together, and I sweat some sweat equity into making this stuff. And the kiddos, we deliver it to them thinking they're going to think this is delicious, and they've got other plans in store. They look at that soup, and the first thing that they notice are these little orange bits, and they go, yeah, I'm not eating that because that is orange. And again, reasons, right? Those little orange bits, the carrots, despite them absolutely adoring carrots, they look in the soup and they think, no, in soup form, carrots, no good. So let's go ahead and we're going to pull those out. And so there's a little back and forth, of course, but then eventually I look on their napkin and I see a pile of orange carrots. And when that happens, those orange carrots being out of the soup is fundamentally changed. It is now a different bowl of soup. It has different vitamins, different nutrients, different calories than it started out as, and those have been removed. They are not going back in. They are not going back in. Looking further into their bowl of soup, they notice these little chunks of squishy things. And despite absolutely adoring French fries and other various forms of potatoes in soup, not happening, right? Not happening. Foot down, there's no way, that's gross, that is coming out of this bowl of soup. I am not eating those potatoes. And again, the soup that's left behind, its chemistry is forever changed. And in addition, the kiddos, despite their extreme fondness for chicken nuggets or you name it, chicken related, the chicken in the soup, maybe it's too what they might call squishy or other terms that I feel like they're making up in this process, but the chicken's got to come out. You just can't have the chicken in the soup. And so again, once that little pile of chicken is there, the resulting soup that's left behind is fundamentally changed. And this absolutely is analogous to what's going on within the magma chamber. A magma chamber is going through a similar evolution. Whereas our soup resulted in these ingredients sequentially being pulled out of the soup, each step leaving behind a different soup. When we turn to a magma chamber and we pull out those ingredients that are utilized to make rocks like peridotite, then gabbro, then diorite, then granite, the iron, the magnesium, the calcium that these rocks contain and have locked into these minerals, it's no longer available for use. So as we see these magma chambers age, they will generally become increasingly felsic through time. And this is a process that we call magmatic differentiation. This is a big one. This is how we get a lot of different rocks out of the same molten mass, is magmatic differentiation. The crystallization and settling out of these more mafic materials takes those ingredients and locks them away for good. And so what we see again is that these materials become increasingly felsic through time. That's one way. One way to get different rocks out of a single magma chamber. Another way is analogous to what you see happen with oil and water. Oil and water have different densities. Oil is a lower density material than our water. That's why when you take some vegetable oil and you put it inside of a glass of water, you're going to see that vegetable oil sit right on top of that glass of water. It has a much lower density. Well, again, those rocks, those minerals that contain more iron and magnesium have a much higher density than our more felsic materials. So within a magma chamber, we can actually see a similar process with what we see with water and oil. We see that can happen within a magma chamber in the different chemistries of the molten materials that are there. That is, in a single magma chamber, you might have mafic materials near the bottom of that magma chamber and more felsic materials near the top. And this image here on the left-hand side here shows exactly that. That is, the deposits that you're seeing there, those are ash flow deposits, and you're seeing light colored materials on the bottom and darker colored materials at the top. And what causes that is the eruption of a volcano will first erupt those materials that are near the top of the magma chamber. So the first thing to come out of this eruption were the more felsic materials, the more silica-rich materials, which are going to be generally lighter in color. As that eruption continues, it starts to tap into deeper portions of the magma chamber, and thus we see more mafic materials extruded. That is evidence, direct evidence of magmatic segregation that had happened in this ancient volcano here, Mount Mazama, which is now the location of Crater Lake. We'll see Mount Mazama come up again in our lectures in the future. Assimilation and magma mixing is our third way of getting different rocks out of the same magma chamber. And the way that this result happens is, or what this does is, this is the addition of new ingredients to a magma chamber. We can introduce new ingredients to a magma chamber by that magma chamber melting the surrounding rock. The surrounding rock that surrounds a magma chamber, that's called oftentimes the host rock or the country rock. Taking bits of that host or country rock and dropping it into the magma chamber, those materials will melt. And as they melt, those elements that they contain are then added to the magma chamber. That's assimilation. Magma mixing is, magma chambers are on the move. They are on the move in the subsurface. That's why volcanoes, they erupt and then they go dormant, then they erupt, right? These erupt and sleep cycles are because the magma chambers they're moving in the subsurface. And sometimes that movement results in magma chambers merging with each other. And once that happens, once a magma chamber merges with another, those ingredients, they mix. So that is magma mixing. So again, answers to Bowens dilemmas, right? What's changing, or what is influencing mineral crystallization? Changes in temperature. Why do we get different materials out of the same magma chamber? Well, it's related to those changes in temperature. It's related to the ingredients that are available. It's related to these things under one of these three scenarios. That's how. So back to the beginning. What's the definition of an igneous rock? Well, it's a rock that forms when molten materials solidify. But if you've ever tried to melt a rock, you know that that's really, really hard. How does the earth do it naturally? Well, there's three ways that the earth does it, right? The earth has a mechanism for increasing temperature. Changes in pressure can result in rocks melting, or we just add water. So that first one there, increasing temperature. How does the earth increase temperature? Are we talking about like a long run of sunny days? No, we're not. Not a long run of sunny days. What we're talking about is utilizing the geothermal gradient. What we talked about when we talked about Earth's interior, that as we go deeper into Earth, temperatures, they go up. And so the geothermal gradient, as we take these materials and put them deeper, they will begin to melt. And so we can do that at, say, a subduction zone, right? Where we take these materials and we drive them down deeper into the earth, they're exposed to ever increasing temperatures. So that's how the earth increases temperatures, through that geothermal gradient. We can also decompress these materials, that is, bring them from very deep to near the surface. As we take materials, if we pressurize them, their melting temperature will be a little bit higher. So if you take and remove some of that pressure by taking those materials and moving them nearer to Earth's surface, that decompression can result in those materials going from a solid to melting to form a liquid. That's something that we call decompression melting. This is what we see at divergent plate boundaries. This is how that magma is forming, that fills the gaps between plates that are moving away from each other. The third way there, we just add water. And we talked about this when we talked about plate tectonics and convergent plate boundaries, both OC-OC convergent boundaries and OC-CC convergent boundaries. We said that it was those minerals that had that little bit of water attached to them. That water coming off of them entered into the overriding plate and lowered the melting temperature of those rocks. And that's what this curve is showing. That red curve there shows the melting curve for, let's look at the purple curve there first. Purple curve there shows the melting curve for dry granite. That is for granite that doesn't have any water sort of in the area, in the vicinity. We see that the temperature for that granite goes up, right? That is, the temperature required to melt that granite goes up with depth. And that's because pressure is increasing. Increasing pressure is going to hold that dry granite together at higher and higher temperatures. That red line there is the melting curve for wet granite. So you can see that by adding water, what happens is that the temperature required to melt that material actually goes down. It goes down, and it goes down as pressures increase. By increasing pressure, you increase the role of water in lowering the melting temperature for that granite. So again, as a bit of oceanic crust subducts below some continental crust, that water is being driven from the plate and then into the overriding plate, where it takes those materials, and it doesn't, that water vapor isn't changing their temperature, but what it is it's changing the temperature that's required to melt those materials. So those materials are sitting there. If we had some dry granite that's sitting there at a temperature at a depth of about 10 kilometers, and it's sitting there at 800 degrees, that dry granite is going to remain as a solid. However, if we introduce some water into the mix, so again, we're at 800 degrees, 10 kilometers in depth, we introduce some water from some subduction. Now that granite is wet, and it will now melt. It will now be molten. And when that happens, that's when we start to see these magma chambers form. So again, one of those scenarios, either increased temperatures through the geothermal gradient, decompression melting via bringing these stuff from very deep to shallower areas within the earth, decompressing them, allowing them to melt, or by adding water. This is how the earth produces that molten material that eventually can form igneous rocks. All right. And once again, as always, I'm here. Bring me those questions. Let's talk about it. If any of this stuff isn't seeming clear, more than happy to clarify anything that needs. All right. So why don't we look at some more igneous rocks? Let's talk about some different igneous rocks and some examples of where they can be seen. This is a piece of granite, again, a really common igneous rock. It's going to have both light and dark colored minerals, and distinctively, it's also going to have oftentimes some pinkish colored minerals in there as well. Those pinkish minerals are going to be potassium feldspar. If you've ever been to Yosemite, much of the rock that's in Yosemite and in the Sierra Nevada mountains in general, that is indeed this granitic material oftentimes. And you might be saying, well, that's intrusive igneous rock. These were all magma chambers, you mean to tell me, Sapling Field? These were magma chambers? And I would say, yeah, absolutely. And then you might say, well, does that mean there used to be volcanoes in this area? And to that, I would also say, yep, absolutely. Absolutely. And if you're interested in that story and those sorts of things, California geology, we go through it in a bundle of detail, but absolutely, the Sierra Nevada, the area that is the Sierra Nevada today, used to look very similar to what we see in the Pacific Northwest with the volcanoes that we see up there today. And these are the exposed fuel cells for volcanoes that used to exist in this area. It's super cool. All right, here's a piece of rhyolite. Rhyolite will have that kind of aphanitic texture, but sometimes we'll also have some mineral grains that we can see with the unaided eye. Oftentimes, those are the more mafic mineral grains. Oftentimes, things like amphibole will make these little shards inside of these rhyolites like this. If you go up to a place like the Eastern Sierra, Mammoth, in and around the Mammoth area, you might be able to find yourself a fair amount of rhyolite there. This is some obsidian. Again, it forms via rapid cooling. Again, there's lots of this stuff in the eastern portion of California there, just east of the Mammoth Lakes area. There's a mountain range called the Glass Mountains. Lots of obsidian in those mountains, and distinctively obsidian with this glassy texture behaves very similar to quartz and will make this conchoidal fracture that we talked about last time, or when we talked about matter and minerals. Here's a piece of pumice. This is, again, each of these little bubbles here, the vugs in this represent the former locations of little gas bubbles that were trapped in this molten mass. This stuff's kind of fun. It's so porous that you can actually, with some examples of pumice, if you put it in water, it'll float. And so in the Mammoth area, there's tons and tons of pumice around. And one of my favorite things to do with the kiddos and on field trips is to grab a handful of that stuff and throw it on the water, and it all just kind of floats. It's kind of cool. It's neat stuff. Also, obviously used for skincare and that kind of stuff. Here's a picture of the Glass Mountains. It's just east of a former volcanic area called the Long Valley caldera. The Long Valley caldera has experienced volcanoes in the area have erupted quite a few times over the last thousands of years. The last big eruption of the Long Valley caldera was around 760,000 years ago. You can find ash and dust from this eruption all the way to Nebraska, all the way down into Mexico. Huge eruption less than 1 million years ago in the area. And you find a bunch of these extrusive igneous rocks in this area as a result of it. And again, field classes, we go out here all the time, we explore these rocks. It's a ton of fun. Here's a piece of andesite. Andesite has oftentimes has a porphyritic texture that is both small mineral grains and large. It's an extrusive igneous rock, but oftentimes it'll have these large, you can see those little white blebs in there. Those are plagioclase feldspar crystals in there. So again, indicating that kind of two-stage cooling that we mentioned for these porphyritic rocks. That name, andesite, andesite speaks to there being a lot of this stuff in the Andes Mountains associated with what are called andesitic stratovolcanoes, big volcanoes there. They're in the western portion of South America. Another really common rock that we have here in California is a rock called diorite. Diorite kind of diagnostically has this what we call salt and pepper coloring to it, right? It is dark and light, right? Salt and pepper kind of coloring to it. Lots of plagioclase in our diorite, along with some mafic materials in there, or more mafic materials in there as well. If you wanted to find some of this stuff, a trip to our San Gabriel Mountains, there's lots of diorite out there. Diorite looks very similar to granite, but it'll lack that potassium feldspar that's contained in the granite. So you won't see those same pink minerals that you would see in the granite. We've seen this picture a few times. Basalt. Basalt, again, is the stuff that a lot of the seafloor is made out of. So we see it come out of a lot of volcanoes, volcanoes that are either out in the ocean or volcanoes that are out in rift valleys. We talked about, remember, those rift valleys and those volcanoes that form in those depressions, in those rift valleys. We noted that those volcanoes are they're extruding like new seafloor type materials, this very dark colored lava. That is basalt, an extrusive mafic igneous rock. Another place where you find lots of basalt is on the islands of Hawaii. The volcanoes on the islands of Hawaii, they extrude this basaltic magma, or excuse me, lava, that oftentimes, again, is adding on to the island, building new island when this stuff enters the sea there. And again, it has a chemical composition very similar to what we see along the seafloor. Awesome. So to review, Bowens reaction series provides us with the sequence of crystallization that happens within a molten mass as it relates to changes in temperature, and thus gives us this ingredient list that we can utilize to determine the relative proportions of different minerals that we find in different igneous rocks, both intrusive and extrusive. So we have intrusive and extrusive rocks that have the same exact chemistry, but are only differentiated from each other based on their texture, right? Based on their texture. That's what makes these rocks different types, right? And so we're going to continue our discussion of igneous processes as our modules continue in discussing volcanic hazards and volcanoes and the different types of volcanoes that are out there and all sorts of exciting things. But that's for the future. For right now, once again, I'm going to encourage you all, if you have any questions at all, please don't hesitate to get a hold of me. Please utilize those Canvas resources. Let's get this stuff all making sense to you let's make sure that you're knocking this out of the park the way that you want to. So until next time, once again, take care of yourselves. Be safe out there. And we'll see you back in here with more exciting topics very soon. All right, everybody, take care.